Just before the midterm, we looked at the distribution when the random variable had distinct or discrete values. Now let's look at the probability distribution when the random variable can take any value within a continuous range. Examples could be the amount of rainfall a region receives in a year, or diameter, the measurements on parts, drilled hole, or thickness of a plate, or it could be time until failure. So how do we describe the distribution of a continuous random variable? In the discrete case, we were able to give a complete description of the distribution of a random variable and their corresponding probabilities, all the values the random variable could take and what was, the corresponding probabilities for those values. But for continuous random variable, we describe the probability distribution in two different ways. One is probability density function, and the other is cumulative distribution function. Now, probability density function is the area under the curve, right? And as you see, this probability distribution function on the right side of the slide. So like before, the total area under this probability distribution curve should be equal to 1. And if you want to calculate, the probability of the random variable taking on values between A and B, then all we have to do is calculate the area under the curve between A and B, right? So the shaded region is the area under the curve there. Another way to describe let's look at one more probability distribution here. The probability distribution function is indicating that it's a little bit skewed to the left, and that means that the smaller values are more likely to occur as compared to bigger values. And there also the similar concept applies. The area under the curve should be equal to 1, and probability between any two regions is basically the area under the curve between those two values, right? Cumulative distribution function is the probability that x does not exceed a certain value, right? So now every time we want to calculate that random variable x lies between two boundaries, A or B, it becomes very difficult to actually calculate that area given the shape of the curve. So the way we do that is we calculate another curve, which is a cumulative curve. It's cumulating all the probabilities. So it is an increasing function of the values over here. As the random variable values increases in magnitude, so does the function increases and caps out at 1. So the smallest value the cumulative distribution function can have is 0, and the highest value it can have is 1. And when we want to calculate the probability of x lying between A and B, all we have to do is same thing, except when we calculate probability of A, we are taking this area, we subtract it from the total area, we end up with the region in the middle, right? We can also calculate probability of x greater than t. Suppose we want to calculate the probability greater than t, what we need to do is subtract, because we know the total probability has to be 1, so subtract probability of x less than equal to t from 1, and we end up with probability of x greater than t. By far the most important continuous distribution model is the normal or Gaussian distribution. The probability density function of a normal distribution is a well-known bell-shaped curve, and the distribution can be characterized by two parameters: expected value of the random variable mean and standard deviation of the random variable sigma. and is often written as normally distributed with mean mu and standard deviation sigma. You will also find sometimes the representation as mean mu variance sigma square, where it's equivalent. The PDF, the probability density function, has a number of very important characteristics, as you can probably observe. The high point of the bell-shaped curve occurs at the mean mu center, which means that x, the random variable x, is more likely to take values closer to its mean than far away from mean, right? So as the random variable value moves away from the center, the likelihood or the probability of the random variable taking that value decreases. The bell-shaped curve is also very symmetric about the mean. So random variable x is equally likely to take on a value x or t units from above its mean as it is to take on values t units below its mean. So if we want a value here, we'll see the probability of these 2 points is similar, is same. Now, many uncertain phenomena in everyday life obey, or more importantly, can be approximately made to obey a normal distribution. And that's why this it makes it a very important distribution to study in statistics. Now, how do we calculate the probabilities from a normal distribution? Now, there is one important thing that I want to point out before we actually go into the details of how do we calculate probability is we define a standard normal random variable as a random variable that has mean 0 and variance 1, and that can be defined, z can be defined as, it can be calculated from a normal random variable. So if x is a normal random variable with mean mu and sigma, then subtracting each random variable value, subtracting mean from each random variable value and dividing it by the standard deviation, we end up with another random variable that has normal 0, 1 distribution. And that comes in very handy because since there's no explicit formula for cumulative distribution function, scientists have computed the area under the curve, the probability density curve, of the standard normal distribution to a very high degree of accuracy and for a wide variety of values of the standard normal variable. And and has compiled them into a computations into a standard normal table. So that comes in handy if you want to use the standard normal table to actually calculate the probability values. So as a quick aside, let's look at computing the probability, the cumulative distribution function or CDF of a value 1.63 occurring from a standard normal variable. So how will we go about doing that? So what I have here in front of me is actually the cumulative standard normal distribution table that is available in the back of the book, Appendix A. And what the table is actually telling you is the area under the curve where the standard normal values are given as the first, trying to use a pen on this, but the first value, this value is basically the area under the curve for when the standard normal value is equal to minus 3.99. And similarly going forth, if we want minus 3.9, what the area under the curve is, so we go all the way back across all the columns, the last column which has 0.00 as a second significant digit, and we see that the area under the curve for that value is 0.000048. So similarly, this is the first page, negative values, This is the second page, which has the positive values. So we were tasked with finding out what is the cumulative distribution CDF value for the standard normal variate as 1.63. So what is the probability of that value occurring? So the way we are going to find is we're going to go down across the rows to find out 1.6. Once we hit that, next we are going to find 0.03, because 3 is our second significant digit after the decimal, and look under there, and what we find is 0.94845 approximately. Yes. Similarly, the value for z value less than 1 would be just this value, 0.8413. Z value less than 0 is 0.5. That should confirm with what we have seen, because it's a symmetric distribution with the mean of 0. So half the area is under the curve at 0 point, right? Which is 0.5. The total area is 1. Now, if you have to find value for z less than 1.5 minus 1.55, we can definitely look up in the table, but we can also calculate the value because it's symmetric. We can also calculate what's the probability less than 1.55. So 1.5. So 1 minus 0.939429 give you approximately 0.060. Similarly, or conversely, given the value of the probability, we can also find out what the approximate z value would be, standard normal variate value would be. So suppose if you want to find out what is the z value that corresponds to a probability of 0.60, we look at the values within the table. So we see that it will be somewhere between these two values. And if you look at the corresponding z value, it will be 0.25 between, so 0.25 and 0.26. Similarly, what is the z value corresponding to 0.10? So we go all the way here. 0.10 would be a value between minus 1.2 and the first and second column, which is 9 and 8. So it will be 0.10. Yeah, so it will be here 2.3. So it will be minus 2.33 approximately. Now, armed with information of calculating probabilities from a standard normal distribution, we can now use that information to actually calculate the probabilities from any normal distribution. So any normal random variable, say for example x, that is distributed according to a normal distribution with mean mu and variance standard deviation sigma. Then if you want to find out the probability that the random variable x takes value between a and b, so a less than equal to x less than equal to b, all we need to do is convert it into a standard normal, and the way we can do that is subtract the mean and divide by standard deviation on all the sides of the equation, right? And we end up with expression with in the form of standard normal variate, and then we can calculate that values. Now, what this is saying is that so if we want to calculate a value between, say, a or let's call them with a different, so with c and D, what we need to do is we calculate the cumulative distribution function for D, subtract the cumulative CDF for C, we end up with the area between these two values, which is what we wanted to begin with. Let's take an example. Let's consider the case of issuing an insurance. Now, issuing an insurance, just simplifying it very a lot, consists of two steps. One is underwriting policy, which has the distribution of the time it takes to underwrite a policy could be normally distributed with mean 150 minutes and standard deviation of 30 minutes, and a rating the policy. That also is assumed to be normally distributed with mean of 75 minutes and a rating of 25, a standard deviation of 25 minutes. Now, first task is we want to calculate what is the probability that it takes 120 minutes or less to underwrite. So what we are asking in the first case is underwrite is less than 120 minutes. So we just have to calculate the CDF for this this normally distributed random variable. We know from before that we can subtract the mean and standard deviation from both sides and convert it into a standard normal variate, and then we can look up in the table and calculate the values. So that is part A. So what is part B? Part B is asking what is the probability that it takes more than 25 minutes to rate a policy, right? So what that is asking is what is, if R is the time it takes to rate the policy greater than 25 minutes, what is the probability of that? And we know from before is we want to find the probability of greater than 25, for example. Oh, this is not correct. Let me draw it accurately. Okay. So if we consider the rating distribution, the mean is 75, sigma is 25 minutes. We want to find out what's the probability it takes more than 25 minutes. So it will be somewhere here. So what is the probability that it is more than 25 minutes? So it is what we want is area under the curve here. We know the total area under the curve, because it's the normal distribution, is 1. So we can do is 1 minus this unshaded bit on the left side here. So rating less than equal to 25. And now we know from before we can subtract the mean and divide it by standard deviation to actually get the standard normal variate and use that information to calculate it from the table. Now the third question is asking what is the 95th percentile of the underwriting time. So what is basically it's asking is what is that value, let's call it capital A, which gives the area under the curve to be 95, right? So if we have for underwriting distribution, we have the mean is 150 minutes. We want to find a value which will probably be on the right side of the mean, that the area under the curve, the left of it is 0.95. What is this value? We saw an example of that. We go to the table, look within the table where we get 0.95, look at the corresponding values on the left hand margin and on the top to actually calculate what the A value should be. You can find the answers in the slides to compare and see if you got it correctly. Now, like for discrete random variables, let's consider the case when we have two random variables, x, which is distributed according to normal distribution with the parameters listed here, and another random variable y, also normally distributed. Then a linear combination can be defined as any constant a multiplied by x plus any constant b multiplied by y plus another constant c, right? So any linear combination of x and y, we observe that this newly formed linear combination is a random variable that is also distributed according to a normal distribution, and the parameters of that normal distribution can be derived as such. Now, I will not go into the details of this. We have gone through in some detail when we talked about discrete case, and we can use the same logic here to actually get these values. But it's a neat distribution because earlier we didn't have, or rather I should say, in this case we're finding one more piece of information that we didn't have, is that the newly formed random variable is also normally distributed according to those two parameters. And that's one of the beauties of normal distribution, leveraging normal distribution for the random variables. So using that information, we have the example here. I will not solve the problem for you here, but I'll give you a chance to solve it. There is answers in the slides. So if you want to double check your work, and happy to talk about it if you get stuck. Now, normal distribution is important distribution, but why? And that is because comes from repeating an experiment and averaging the outcomes. The average average of that experiment approaches a normal distribution. So what does that mean, right? So let's look at an example where we have one dice, and we roll it 10,000 times. And what we are interested in is calculating the average of the value that we got on the dice. And what we'll start to see is that we get all the sides. So a dice has 6 sides. The probability of each side turning up is 1 by 6, equally likely. And if we roll it many times, we'll see that we sort of get a uniform distribution, a distribution which tells us that there are 6 possible values and each value is equally likely. And then we calculate the average. We get an average in the middle, which is about 3.5. Now, that's interesting, and that's expected. Now, in case if we have, you get one more friend, and then that friend also rolls the die, and you also roll a die, and repeat the same experiment, and now we're calculating the mean of the the values that you got on the dice, we'll start to see that the values will start to be converging more in the center. So there'll be more values in the center as compared to the edges. And if we get the whole class to do that experiment, and if we do it enough time, then what we'll see is that that it slowly converges. So the average of the values that we obtain on the dice on those rolls tends to converge into a symmetric bell-shaped distribution, converging to a normal distribution. And that is the central limit theorem, and that's why this theorem makes it normal distribution even more have even more importance. So central limit theorem can be described in 2 ways. One, for the sum, where we are saying that if x1 and x2, xn are all independent and identically distributed random variables. They could be distributed according to any distribution. It could be continuous, it could be discrete. It doesn't matter as long as they are independent and they are identically distributed. And each random variable has a mean mu and a standard deviation sigma. And if we have, moderately large n, then the sum of those random variables is a random variable that is approximately normally distributed with mean n mu and standard deviation sigma root n. Now, for those of you who are have advanced mathematical training, I welcome you to derive that and prove it for yourself. The same thing can be applied for the mean, right? So if similarly, if we have x1, x2, xn, which are independent and identically distributed random variable, then if we form a function of those random variable as taking the sum and dividing by the number of random variables we have, which we know as like calculating the average, then that average value can be approximated to be distributed normally with mean mu and standard deviation sigma by root n. And this is a very important theorem, and leveraged multiple times in actually doing experiments and approximating the distribution of those random variables, even though the underlying distribution might be highly skewed or might be highly discrete. There are other useful continuous distributions as well. You can read more about them via the book. I would also recommend Wikipedia as a great resource for learning about these distributions. It's pretty comprehensive as to the mathematical thinking and even the application of these distributions there. The few that I want to highlight are uniform. That's when we assume that each value is equally likely, but can only occur within a bounded interval a and b. The PDF is constant. Each value is equally likely. It is often used in modeling random waiting times, or it can also be used, or it's used very often in computer simulation for random number generation. The other one is exponential. Exponential distribution has been used for modeling failure times. But the unique property about exponential is that it has a no memory property. What that means is that if you're modeling waiting time, so in this instance on the table, right, if you're waiting for at least y more hours for a table to open up, it is not affected by how much time we have already waited, and we could have waited x hours or 0 hours, right? So a probability of waiting y more hours is the same as probability of waiting. It is independent of how many hours you've already waited before. Another distribution that is commonly used in failure times is Weibull. The fourth distribution that I just want to mention is log normal distribution. So if x is normally distributed random variable, then e power x has a log normal distribution, and it occurs, one way to think about it is using the central limit theorem. We see that sum of random numbers approximate to a normal distribution, but if we take a product of those random numbers, it will converge to a log normal distribution.